Yeah, so we're gonna continue and we're switching to the second set of slides, so lecture note 2, in case anybody's following from the files. And our topic today will be looking at the basic conservation laws. So these are the basic fundamentals that we need to study open channel flow, and they're really not different from physics, really basic physics, and also whatever we learned before in fluid mechanics. It includes mass, conservation of mass, or sometimes we call it continuity, includes the conservation of energy. We sometimes call it the Bernoulli. It's not really the Bernoulli equation, but kind of a adjustment to the Bernoulli equation gives us the energy equation. We'll look at that. Momentum, which is coming from Newton's second law. Again, nothing new, just kind of a modified application to our study, which is open channel flow. And then we look at energy losses, and that's includes the Darcy equation and the Moody diagram and so on. Again, it's nothing new. It's from the basic physics that we've already seen, and this is what we will be discussing over the next few weeks. So we'll start with the conservation of mass. What I have here is a longitudinal section of a channel. So the top one is longitudinal section. The bottom one is a cross section. So if we cut a section anywhere along the channel, something like this. Let's say we cut a section here and we look this way. Remember, rule of thumb, you always look upstream to downstream. Let's say flow is from left to right, so that's the flow. And we have flow coming in two sections. Section 1, we have a flow of m.1 mass flux of 1. So I'm going to write here m dot is mass flux. So it's the rate of mass passing through a section, how much mass is passing per unit time. So that's M1 coming in at section 1, M2 going out at section 2, And let's say the density of the fluid at section 1 is rho 1. So we have rho 1 here and rho 2 at section 2. And depth of flow is Y1 at section 1 and Y2 at section 2. So a bunch of definitions for now, nothing new. And what does the conservation of mass say? Conservation of mass says if you're not generating mass or losing mass between section 1 and 2, which, by the way, we call the control volume in fluid mechanics generally, if you're not losing mass or creating mass somehow, then mass should be conserved, which means whatever comes in, m.1, should be equal to whatever goes out, m.2. So as simple as that. That's mass conservation of mass. So what is m? M dot is mass flux, which is equal to rho q, density times q. What is q? Q is the volumetric discharge or rate of flow. So it's volume divided by time. So you can do, that's very simple. You can do the math. If you multiply volume by rho, you get mass. So m dot is mass per unit time, is mass flux. Okay, so conservation mass says m dot 1 is equal to m dot 2. Okay, let's just plug in the equivalent equation. So it means rho 1 q1 is equal to rho 2 q2. Okay, nothing new. Now we're going to say if rho 1 is equal to rho 2, what does that mean? Density of the fluid does not change from section 1 to 2. What does that again mean? That means the flow is incompressible. So I'm going to write in brackets. Flow is incompressible. So if you cannot compress the flow, the fluid, it means its density doesn't change. So rho 1 is equal to rho 2. So again, going back to the equation up there, that means if rho 1 and rho 2 are equal, that means Q1 has to be equal to Q2. So Q is, I'm going to write it here again, Q is volumetric flow rate. Again, it's a definition, or sometimes we call it discharge. I'm going to write that too. Sometimes we just say discharge, and we might use that a lot from now on. Just keep in mind, whenever we say discharge, it means this volumetric flow rate. We're going to continue and try to be consistent and use capital Q, but if it's a different letter use, it's the same thing, discharge volumetric flow rate. Okay, so conservation of mass says if the fluid is incompressible, so density doesn't change, then discharge won't change from section 1 to 2. And remember, the requirement is, the condition is that we're not creating mass, adding mass, or losing mass. So this is one channel. We don't have a secondary channel coming in or going out between 1 and 2. So we're not adding mass or losing mass. Okay, so that's good. We already know that discharge or volumetric discharge is equal to area multiplied by velocity. We already know that, all right? So another way to look at the conservation of mass, as we just found it, is, again, just plugging in A1 times V1 has to be equal to A2 times V2. So again, this means if we have A1, V1 at section 1, A2, V2 at section 2, if velocity goes up at section 2, area has to go down, and the other way, in general. Again, in general, we're looking at a simplified case. Okay, so let's look at this from a little bit of a different perspective now. So let's say we're looking at the section. Okay, that's the water level. This is the depth. Typically use Y for depth, so that's depth. And the width of the channel, it's a rectangular, simple rectangular channel. For simplicity, we're going to keep it like that. And the width is B, capital B. All right. So let's look at this from the section kind of standpoint. So what do we have? We have discharge at section 1 has to be equal to discharge at section 2. By the way, it's obvious, but we are assuming that there is no change in channel geometry from 1 to 2. So everything is the same, except for flow properties like velocity and area and depth potentially. But the geometry is not changing. We will look at that later on, but for now, we're going to assume that the geometry is the same. So discharge at section 1 is equal to discharge at section 2, Q1, Q2, which means A1, V1 is equal to A2, V2, nothing new. All right. If it's a rectangular channel, what do we have? Area in a rectangular channel is as simple as width times depth. That's it. So I'm going to say B times Y1 times V1 is equal to B, the same width. Again, the channel geometry is not changing. That's what we're assuming. Actually, I'm going to write in a general form for now and then add that as a condition. So B2, Y2 times V2. And then I'm going to say if B1 is equal to B2, in other words, the channel geometry doesn't change. It's rectangular and the same width. Then what do we have? From that equation, obviously, B will cancel from both sides. So we will be left with Y1, V1 is equal to Y2, V2. Yeah, just a modified version of the same equation. So what is the difference between the top and bottom one? I'm going to write it. I'm going to say this one is all channel, the previous one that we looked at, all channel geometries. We never really mentioned anything about the geometry up to that point, but this rectangular one, the red one is for rectangular channels. For rectangular channels, and we're assuming the width doesn't change. So I'm going to say rectangular channels. Why do we keep saying or using rectangular channels? As I said before, first of all, they're relatively common. Second, they're relatively simple geometries. A lot of the equations are way easier to establish in rectangular and then expand to other shapes, which is exactly what we'll do. But we'll start with rectangular to make it easier to derive equations and look at them. Okay, now, if you recall, another definition we had earlier was that if you take the total volumetric discharge and divide it by the width of a rectangular channel, you get a small q, which we call the specific discharge. A specific discharge or unit discharge, or you might hear other terms but it's really the same thing. It's total discharge, volumetric discharge, divided by width of a rectangular channel. Again, this is for rectangular channels. Okay, if we do that and go back to the equation we just saw for rectangular channels, what this means is that I'm gonna draw an arrow here. This means that your specific discharge, conservation of mass says, your specific discharge, small q, has to be the same. Why? Because the width is the same. So if capital Q is the same, then small q has to be the same. So this is, again, I'm going to highlight this is only for rectangular channels. But the conservation of mass reduces to a relatively simple equation, and it's really discharge being the same. And in rectangular channels, even simpler, specific discharge. We don't have to worry about width. It's the product of depth by velocity that has to be constant. So really not much different from general conservation of mass. Now, a kind of a side note I'm going to briefly mention here because I think it's worth discussing here. And that's about unsteady flows. As I said, we won't really discuss unsteady flows much. I might be mentioning here and there unsteady flows, and hopefully at some point we'll discuss it a little bit more detail, but in general, we won't get into too much detail of unsteady flow in general. But a quick note on unsteady flows. So what if we have an unsteady flow? A very common case of unsteady flow is whenever we have waves. Remember, unsteady flow means variation with time. So I'm going to say derivative with respect to time is not zero. Derivative of what? Derivative of flow properties, like typically depth and velocity are the ones that we look at. But derivative is not zero with respect to time. So waves, obvious one. When you have a wave, things are changing with time. Another kind of category under waves is flood waves. Floods are really waves, but they're much longer wavelength and much longer durations, but they're really waves. Flood comes in, water level really goes up, takes much longer than what like an ocean wave, typical ocean wave would look like, but it's the same concept. Now, what happens when we have waves? Let's see what happens. So I'm going to sketch a tiny channel here like that. And I'm going to show a wave. So it could be any kind of wave, but let's say it's a flood wave. So water is coming in at some point because of the wave, we get more flow, depth goes up, and then at some point downstream, nothing is happening, everything is still normal. If this is a natural river, let's say the Fraser, let's say there's a flood and we know that the flood has arrived at Hope or somewhere upstream, it's going to take some time for the downstream reaches to even see that the water level is changing and the discharge to go up, but that could take time. Now, what's happening here? First of all, we have this wave, and the wave is traveling at a celerity of c. Remember, we talked about this one too. And the general flow is from left to right, just to establish some orientation here. And what's happening here? The wave arrives at some point. This is Hope or something, and then, oh yeah, depth goes up. The flood arrives. We get a depth of y1. And the discharge goes up because the flood is coming in. So we have a discharge of q1. But farther downstream, depth is y2. The flood has not reached there yet. And the discharge is the normal discharge in the river, whatever it was, it's still there. It's going to go up at some point when the flood arrives, but we're not there yet, right? So this is, okay, what happens if we have unsteady flow like this? First of all, the first thing you will notice if you're looking at section 1 and 2 is that discharge at section 1 is not equal to discharge at section 2. And that's another kind of challenge we have with unsteady flow. Remember in the previous slide, when we talked about conservation of mass, we said discharge, we ended up with discharge being constant. We never said that, but it was a steady flow. In unsteady flow, it is not the case. Discharge is different. Now, how do we study this? How do we look at a case like this where it looks like things are a little bit different and maybe whatever we discussed before, not so easily applicable. First of all, I'm going to assume that our coordinate system here is fixed to the bed, and this is our x-axis and this is the y-axis. right? That's very common. That's what they typically do. And one challenge we have is things are changing with space and time. As we said, when things are changed with time, when we have unsteady flow, things will change with space too. So we also have non-uniform flow, right? And if you're, let's say this is a river, you get a chair and you go sit by the bank along the river and you watch the flow and you see that, oh, water level is slowly going up and then slowly goes down after the wave passes, right? So things are unsteady. Now to study this, again, we have some challenges. Things are changing with time. But in some cases, especially these type of waves, which are relatively, oops, let me go back, which are relatively long duration, slow. There are changes with time, but they're happening gradually and relatively slowly. Remember, we categorize this type of flow as quasi-steady, meaning that they're not steady, but changes with time are not super fast either. So we can assume they're kind of steady. How do we do that? In cases like this, what we can do is we can actually make an assumption, and hold on, I'm gonna try to get my cursor to work here. We can make an assumption and do this. So I'm gonna say first of all, we can't do this simplification for all unsteady flows, but some of these unsteady flows, and which ones are these? These are the ones that are quasi-steady, meaning that changes are not super fast with time. Unsteady problems can be easily transformed from unsteady to steady by changing the perspective of the observer. What does that mean? So again, if this is a natural river, you're sitting there, a flood comes in, you get a chair, you sit there, watch the flow, water level goes up with time, you look at it at 2 p.m., it's nothing happening. At 5 p.m., water level goes up by half a meter and you keep watching, right? So in this case, we are using a coordinate system, the one I have up there, which is attached to the bank, which is not moving. It's stationary. Now we can make things different. We can look at it from a different angle. We can actually do this. We could say, okay, that's my channel. And this is the water level, okay, unsteady, so things are changing with time. Now I'm going to do this. Instead of using that stationary coordinate system attached to the bank, like that chair you have sitting on the bank, attach it to the wave. Attach the coordinate system to the wave. Something like that. So what happens now? First of all, this means like you get a boat and you sit at the top of the apex of the wave and you just travel with the wave. Now you can imagine if that's the case, if you're attached to that point or you're traveling with the wave, you're traveling at the speed of c. So it's like nothing is changing with time. If you're that in that boat attached to this wave going at the speed of c, nothing changes for you. So things become steady. That's why we say this is quasi-steady. The phenomenon itself is not steady, but with a relatively simple transformation, we turn it into a steady case. For example, so I'm gonna say it here. For example, the coordinate system, mathematically, that's what we're doing. We're attaching the coordinate system travels with the wave. Travels with the wave. Now, there are some assumptions we're making, and they're kind of obvious. For example, somebody might say, yeah, the shape of the wave doesn't remain exactly the same. So even though we're traveling with the wave is really changing. Yes, that's why we say quasi-steady. And again, this is just an attempt to make unsteady flow a bit easier to study. Otherwise, it will be very difficult. It will be a little bit more challenging, right? So there are some assumptions and some simplification that we're doing, obviously. But again, that's an attempt to make it manageable. So just a side note on unsteady flows, but keep in mind in unsteady flows, the conservation of mass does not require Q1 being equal to Q2. They could be different. Still, we're not generating mass or adding mass or withdrawing mass between section 1 and 2 in a way, but Q1 is not equal to Q2. So keep that in mind. Okay, let's move on to the energy, conservation of energy. And then this will lead to kind of an application of the Bernoulli equation in a way. So let's just sketch again longitudinal section of a channel very quickly. So that's the bottom of the channel. This is the, let's say, the water level. That's where the water level is. And let me quickly adjust this. Yeah, so that's the water level. I'm gonna pick a datum because I'm gonna need a datum for the elevation, remember? So I'm gonna say this is our elevation datum. Okay. And I'm gonna pick a couple of sections. Let's say section 1 or point 1 somewhere here is located at an elevation of Z1. Another point farther downstream at an elevation of Z2. Okay. Remember from the Bernoulli equation, we have three terms. We have elevation, we have pressure, and velocity. Pressure, if it's hydrostatic, it's simply the height of the water column above that point. So at section 1, it will be P1 over gamma will be this distance. At section 2, it will be this much. P2 over gamma. That's the pressure head. And then finally, we have the velocity head. And it's going to be somewhere here. It will be this much velocity head at section 1, V1 squared over 2G. And this much velocity head at section 2, V2 over 2G, squared over 2G. And again, just a reminder, this line at the top is called the energy grade line, EGL. And the sum of the pressure and elevation head is called the hydraulic grade line. And if the pressure is hydrostatic, it coincides with the free surface. That is what I'm showing here. Okay, what does the Bernoulli equation or later on the energy equation say? It says at section 1, you have three terms. You have the pressure, elevation head, pressure head, and the velocity head. The sum of these three terms has to be equal to the same terms in section 2, elevation, pressure, and velocity. And typically we call this the capital H value or total head. I'm going to write it here. Total head. And it really says it's constant. So the Bernoulli equation says as you're traveling with the flow, your total head remains constant. This is what we call the Bernoulli equation. Sometimes we use the abbreviation BE, just a reminder. So again, a reminder, what was total head? If you do the math and go back and look at these terms in more detail, you'll see that the total head, I'm going to write it here, total head, capital H, is really equal to the energy divided by the unit weight of fluid. If you want to kind of back check it against what we have in the physics and maybe solids, that is what it is. It's the energy of divided by unit weight of fluid. That's what it is. And unit weight of fluid in case of water is gamma. Water, you should know this, but it will be equal to 9810 newtons per cubic meter. Let me fix my N so it looks like an N. There we go. Right? So the total energy is really, the total head is really total energy divided by the unit rate of flow. So nothing new. Now we can change our perspective a little bit. Now that we're focused on open channel flow, we can make things look at things a little bit differently. So let's do that. We're gonna say, okay, the same setup, exact same setup. We have flow from left to right. So from going 1 to 2, I'm gonna show it here. That's our flow. That blue line is the water level, right? And at section 1, if that's our datum, that line is our datum. So I'm gonna actually extend it. We have an elevation of Z1. But what I'm doing here, what is different here is I'm picking the representative points at the bed, at the invert of the channel, because we never said we cannot do that. There's really nothing that prevents us from doing that, right? So let's do that. I'm going to assume point 1 is at the bed, point 2 is also at the bed, at different station, but at the bed, right? And apply the Bernoulli equation, see what we get. So elevation, easy. Pressure, just like before, it's equal to the height of the column of water above that point, assuming if it's hydrostatic. So it will be this much. So it will be P1 over gamma. But look at this. What is this? This is equal to depth. So it's equal to depth 1, Y1. The same thing here. Pressure head will be equal to this much, P2 over gamma. And again, if pressure is hydrostatic, this is equal to depth. So a little bit simplification, right? Velocity, and by the way, this will be our HGL as before, nothing new. Velocity is not any different from before. It will be, let's say it's this much, V1 squared over 2G. That's the velocity head, not the velocity. And then the same thing here, V2 squared over 2G. And then if we sketch a line, we get this line, which is EGL, right? So what did we do? The only difference really here is that by moving our representative point to the bottom of the channel, this is what happened. We said pressure at that point, or pressure head at that point, is P over gamma, just like before. But pressure is what? Pressure is gamma Y. It's equal to weight of the column of water above that point. So it's gamma of water type, or liquid, I should say, multiplied by depth, P over gamma, and this is obviously equal to Y. So the pressure head is equal to Y. That's the simplification we got. So what do we have for section 1? We have Z1 plus Y1 plus V1 squared over 2G, okay? And at section 2, we have Z2 plus Y2, that's our pressure head, velocity head, no change just before, all right? So that's what we have. Now, let's assume that we have a loss in total energy or change in total energy of this much. So we're going from section 1 to section 2, and the drop in EGL is equal to HL, head loss. So just that definition, nothing new, all right? And let's see what happens with this. Obviously, I'm going to write it here. H1, as you can see on the screen, actually, let me highlight it. This is H1, total head at section 1. And this is H2. It is obvious that H1 is equal to H2 plus whatever that HL is, at loss, let's call it. Right? Now, also, let's look at this from this angle. Also, we'll see that, yeah, that's the obvious conclusion from here. I'm going to highlight this, and we're going to come back to this in a second. But also, I'm going to look at this. I'm going to say the drop in, or the change in elevation, not necessarily, let's say just drop in elevation is this much. Just keep it in mind. We're going to come back to this delta Z, right? So nothing new. All we did is we moved the point to the bottom of the channel and rewrote the energy equation or the Bernoulli equation, and we ended up with a little bit of a different setup for our equation. Just keep in mind two things that we've assumed so far. We assume the flow is steady, which is what we're going to be discussing most of this class, if not all of this class. And also, remember when we said P over gamma is equal to Y, we are really saying that the pressure is hydrostatic. We discussed this last time. If the pressure is not hydrostatic, we cannot make that assumption. There will be more terms, kind of correction terms in the pressure, but we're going to ignore them and assume we have a flow in which the pressure is hydrostatic. Okay, so nothing new, really. We just modified the Bernoulli equation. We ended up with a slightly different form by just moving our points. Now, before we continue looking at that Bernoulli equation, let's look at a scenario comparing pipe flow to open channel flow. Okay, so what I have on the screen is pipe flow. Flow goes from section 1 to 2. The diameter of the pipe changes from D1 to D2. Obviously, D2 is smaller. As a result, the area of the flow changes from A1 to A2. Conservation of mass, just like before, no changes. It says if it's a steady flow, Q1 should be equal to Q2. Okay, and let's say we have this, we know the discharge, and we want to know the velocity at section 1. Or we want to know the velocity at section 2. What do we do? If you have the discharge or we have the diameter or both, it's as simple as velocity being equal to discharge divided by area, and velocity at section 2 will be the same thing. So this is from a pipe flow, pressurized flow. What is happening here? Well, as we discussed before, in pipe flow, pressurized flow, one kind of simplification we get is that the area, the geometry of the conduit is equal to the geometry or section or area of the flow, meaning that if the diameter goes down, if the area goes down in the pipe, the area of the flow will also go down in the pipe. That was something that we knew already, right? So why are we mentioning this? Now let's look at the similar case. And here we have an open channel flow. This is again a longitudinal section. We're looking at this. Obviously, this is an open channel flow, so we don't have a top for the channel. It's just the bottom, the invert that we have. At section 1, we have y1, depth of 1, and velocity head v1 squared over 2g. Section 2, what happens? The bed is raised by delta z. So I'm going to write that down. At section 2, XS2, bed, the channel bed is raised by delta Z. What does that mean? In a way comparable to changing diameter of the pipe, right? If you compare the left and right, it's almost like the one on the right is half of the pipe flow on the left. In a way, similar, not identical, but similarities there, right? So what's happening? At section 1, we have an area of A1, we have a discharge of Q1, an area of A1. At section 2, we have a discharge of Q2, an area of Y2, right? We know that from continuity, we saw that earlier, or conservation of mass, Q1 has to be equal to Q2. That's something we know. Okay, that's good. Let's see if it's as simple as pipe flow. Now, one challenge we have in open channel flow is the fact that because the channel, the flow geometry, the section shape and geometry and size and area is not necessarily equal to the channel geometry. What happens here is that, okay, the bed goes up by delta Z, the water level will change, but unlike pressurized flow, we don't know how it will change. In other words, it might do what I have in this dashed line here. So the water level may end up being here. Maybe, I don't know, I put a question mark. Or it might do something else because there's nothing to stop the flow to do this, to go actually up, right? Maybe it goes up there because there's no wall, there's no pipe wall to stop the flow. It could be anywhere, unlike the pipe flow, right? So I'm gonna write it here because it's very important. In this open channel flow, Y2 is not necessarily equal to Y1. So at section 2, unlike pipe flow, Y2 could be anywhere. It could go down, it could go up, it could be anywhere. And remember, this is because of the fact that by almost removing one half of one side of the wall, the top of the walls, we are adding 1 degree of freedom to the flow. So as a result, if that's the case, if I don't know where the cross-section of the flow will be in section 2, then I don't know what A2 will be. So I don't have A2. If I don't have A2, then I don't have Y2. If I don't have Y2, then I cannot calculate V2. Unlike the pressurized flow, the pipe flow. That was easy. If you gave me the diameter of the pipe at section 2, I could give you the velocity. If I had velocity and area upstream. But here, if I give you a velocity and area upstream and give you delta Z, still you cannot, as of now, yet, we haven't learned that yet, we'll do that. But so far, we are stuck. We don't know what the depth of the flow will be. Now, this is what is called the transition problem, the channel transitions. In a similar pattern, it could be side walls of a channel too. Like if instead of this, we look at plan view and the width of the channel changes, it's very similar. It's a similar situation. So it's called a transition problem in open channel flow, meaning that if the geometry of the channel changes, the flow will change. But unlike pipe flow, it's not like we can say, oh, the channel bed went up by delta Z, so depth will go down by delta Z. No, we cannot say that. We need to study that in more detail. And that's because of the fact that there is 1 more degree of freedom in open channel flow because the top is free to move, can go up and down, the free surface. All right, so let's see how we can study this. This is something very important, obviously, and it looks like whatever we know so far isn't sufficient. We need something else, right? So what this has been kind of covered under is the idea of what is called the specific energy. So we looked at energy or Bernoulli, and we know what the total energy and all of that is, right? So we need a little bit of modification, a very minor modification to the energy equation to be able to solve the transition problem type problems. Okay, so what is that? Let's start with some assumptions. We're going to assume that we have uniform flow. And for simplicity, I'm going to also assume that we have a rectangular channel. Again, just to start with, to keep things under control. So rectangular channel, uniform flow. So uniform flow, by the way, means what? Uniform flow means that velocity is constant with the space. So velocity doesn't change with the space. That's the definition of uniform flow, right? So very quickly, the same sketch as I had before. I'm gonna extend our datum. So what do we have? Section 1, very quickly, we have elevation head Z1. Section 2, we have Z2, right? We have pressure head of, this is the water level, of Y1 and Y2, which, by the way, gives us the HGL. I'm gonna write it here. And then also we have the velocity head, nothing new. Velocity head V1 squared over 2G, and velocity head here V2 squared over 2G, and the line connecting them is EGL. Let me fix this. Okay, as we showed you before, let's say we have a drop in our total energy line, or the slope of the energy line being HL, something like that, or delta H, doesn't matter, right? And also the difference in bed elevation between the 2 points is delta Z, which is equal to Z1 minus Z2, right? Okay, so let's simplify and see what we get what we have. So first of all, we have uniform flow. So I'm going to write it here. Uniform flow means V1 is equal to V2. Okay, so let's look at continuity now. From continuity, what do we have? We saw continuity earlier. Continuity says small q is equal to small q at section 1 and 2, rectangular channel. If B doesn't change, if the width of the channel doesn't change, again, we saw this earlier, it means, and velocities are the same, it means depth won't change. Y1 is equal to Y2. Okay, so what do these mean? Let's look at them in a little bit more detail. So Y1 is what? Or depth is what? Depth is distance from HGL to the bed, right? That's what it is. So if Y1 is equal to Y2, the distance from HGL to bed doesn't change. What does that mean? It means the bed is parallel to HGL. That's what it means. Okay, that's good. And also, the first one says uniform flow, so velocities are equal. So velocity heads will be equal. So distance from EGL to HGL will also be the same, won't change. So HGL will be parallel to EGL as well. In other words, in uniform flow, we'll have parallel the HGL, the water surface, and EGL, the energy grade line, will be parallel to the bed. So, okay, let's look at it from a geometric standpoint. What does that really tell us? If these three lines are parallel, what happens? If the bed goes down by delta Z, the AGL has to go down by the same amount because they're parallel. If one goes down or up, the other one should go down or up the same distance. In other words, delta H has to be equal to delta Z. That's the big finding here, right? So what we are trying to find here is that so the bed changes, is the slope, it's gravity flow, it's a sloping, goes up or down. Let's say it goes down. It could go up, by the way, we'll look at that. But let's say it goes down by delta Z. And because we have uniform flow, depth doesn't change. So HGL goes down the same distance, the same amount. And because uniform flow velocity is the same, velocity heads are the same, EGL has to go down by the same amount as well. So delta H and delta Z are equal. So the bed goes down, EGL and HGL follow that. They remain parallel. So what is the finding? How does that help us? So if we compile all of this into the concept of what we call specific energy. So what is that? So I have this section here. For simplicity, we're showing a very mild slope. It's still sloping, but for sake of what we're looking at, we'll look at a simplified case. So let's do this. Let's say, okay, if the bed and EGL and HGL are all following the same line, and EGL goes down, bed goes down, they're following the same. So why don't we do this? Why don't we move the elevation datum to the bed? So let's do that. I'm going to say, I'm going to move the channel bed. I'm going to move the datum, elevation datum to the channel bed. Why do I do that? Then I don't have to worry about elevation. Why and how does it help us? Because remember in the previous slide, changing elevation is equal to changing EGL. So I don't need to, that's redundant. I already have EGL. I can look at EGL and that's going to give me changing elevation or delta Z. So let's, in a way, ignore it. Let's move the datum to the channel bed. So what happens if we do that? If we do that, in section 1, we have a depth of Y1, section 2, we have a depth of Y2. Okay, nothing new. We have velocity heads of V1 squared over 2G and V2 squared over 2G. Okay, and if we connect them, we get the EGL. And by the way, the water surface is HGL, assuming hydrostatic pressure. Right? And what is the new definition, the new concept that we are defining here? We're saying that our total energy at section 1 is equal to this height, is equal to E1, and at section 2 is equal to E2. What are the conditions? How are we defining these E values, which we call this specific energy? These are total heads with respect to a datum which is located or coincident with the bed, with the channel bed. In other words, we are ignoring change in bed elevation. So as a result, E1 will be equal to what? Will be equal to Y1 plus V1 squared over 2G, and E2 will be equal to Y2. Obviously, we don't have the elevation because that's gone. That's equal to the channel bed, so it's really ignored in a way, right? Now, okay, if we do this, if we have uniform flow, what happens? if we have uniform flow, remember these all 3 points, 3 lines, bed, HGL, and EGL are parallel. So if you have uniform flow, Y1, Y2 are equal, V1, V2 are equal. So that means the total height from the EGL to the bed, which is E, won't change. So E1 will be equal to E2. So that's the big finding. So what did we do? We said, okay, let's redefine energy by a very, very minor change, by moving the elevation datum to the channel bed. Why do we do that? Because a couple of things happen with that. First of all, we don't have to worry about the elevation change anymore, the bed elevation. Second, if we have uniform flow, we find something very helpful, very, very interesting and helpful. We'll see later how it helps us. But the fact that because of the energy equation and what we saw in the Bernoulli equation, energy to total head is constant, the specific energy will be constant, and it will be the sum of these two terms, the pressure head, which is depth, and velocity head, only two. We don't have elevation anymore, right? So this minor change is very, very helpful in dealing with open channel flows and the transition problem, which we'll look at that. But before we get there, let's look at this this new form of the energy, which we call the specific energy, and see what is it exactly telling us and what's involved, and how do we deal with the equation and so on. So I'm going to focus on again, rectangular channel for simplicity, and see what does the specific energy equation look like in a rectangular channel. So that's a section view of a rectangular channel, of course. And for simplicity, we start there again. And let's say that's the water level inside the channel. The channel or the flow has a depth of Y, and a width, the channel has a width of B. Okay, let's look at our specific energy equation and see what happens now. So the specific energy equation was what? We just saw that. E equals only two terms, depth plus velocity head, V squared over 2G, right? So if we have a rectangular channel, I'm going to try to simplify or look at this from a different perspective. If you have a rectangular channel, what happens? Rectangular channel, Q is equal to V times Y, right? That's the unit discharge. I'm going to write it in brackets, how we got there. Small q is equal to capital Q divided by B. Capital Q itself is BY times V divided by B. So it will be equal to V times Y. That's how we got there. Okay. Now let's see, how does it help us? Let's plug this back into the specific energy equation. So I'm going to do this and see what we get. So the specific energy equation will be equal to Y, doesn't change, the same thing, depth, plus, instead of velocity, we can take velocity and replace it by Q divided by Y, but it's a square, right? So let's do that. So I'm going to get Q squared over 2G left over from the velocity head, and Y squared because V squared, right? That's what we have. So I'm going to highlight this one. This is the second form of the specific energy equation for rectangular channel. I'm going to highlight the first one too, because that's a very important equation too. That's 1 and then 2. So 1 and 2 are two forms of the specific energy equation. 1 is for all shapes, but 2 is only rectangular channels. Just keep in mind. Only rectangular channels. All right. So let's see what is happening. What is happening here? What are the terms that we have in this equation? It's not new. We've already seen that. But the first term, depth, guess what? Comes from pressure, hydrostatic pressure, right? So it's a pressure term, really. It's very comparable to the Bernoulli equation, so nothing new. And the second term, just be careful that, yeah, it has discharge in there, but it's really another form of the velocity head. So nothing new, really. This is also the velocity head. So everything is very much comparable to the Bernoulli equation or the energy equation, whatever you want to call it. It's the same concept, right? So we have two forms for this new form of the energy equation, which we call the specific energy. One is using velocity. The second one is the same equation, but using discharge. Now, you might ask, okay, why do we prefer, or why do we show the one with the discharge? We'll see that it will become very obvious in our next class, but it's because discharge, remember in conservation of mass, discharge typically is constant in, well, it is constant in steady flow. So that numerator in the second term, Q, is constant. So by replacing V with Q, we are really changing the equation from a two variable equation, V and Y, into a single variable, only Y. So that's the big advantage, because Q is typically constant, so we don't really have to worry about it. Now, okay, what's the next step? Let's just study this equation, and let's start by, now let's plot this equation. Let's plot this equation. How do we do that? Let's plot it as E as a function of Y, because that's what it is. E, specific energy, is a function of Y. Now we'll see, well, this is a very important plot, and it will teach us a lot of things. So that's very important. I will continue looking at this next time too, but let's just start looking at this equation. I'm going to write the equation again one more time. E was equal to Y plus Q squared over 2G Y squared. And we're plotting Y against E, or E against Y. Typically, for simplicity, we keep Y on the, well, that's not a straight line. We keep Y on the vertical axis because it's depth, it's easier to visualize. And we keep E on the horizontal axis. That's very common. You might see some references which they have these the other way, but doesn't really change anything, right? So let's look at the equation we have. Let's rearrange this equation a little bit. Multiply everything by y2. So I'm going to have EY times, sorry, E minus Y. E minus Y. So I'm taking Y to the other side and then multiply by Y squared. Will be equal to Q squared over 2G. And again, as we said, conservation of mass says Q is constant. So Q squared and G is constant. So Q squared over 2G for the uniform steady flow will be constant. So I'm going to say this is a constant, and it's a positive number. G is positive, Q squared is positive. So it's a positive number. So I'm going to say it's a positive number as well, right? So, and by the way, this is for a given unit discharge, obviously, right? So we're only looking at one fixed value of Q, or discharge, right? So in other words, if you're plotting the EY graph, we have to do that for different Q values, for discharge values. So let's look at it from a little bit of a calculus here. So as Y approaches 0, what happens? Then Y squared will approach 0, right? Then E minus 1 will approach infinity. So that means E will approach infinity. Okay, so what does that mean? That means Y equals 0 is a horizontal asymptote of the graph. It's gonna be coincident with the E axis, but I'm gonna show it tiny bit below just so that we know it's there. So this is a horizontal asymptote. And again, remember from calculus, asymptote means as you're approaching that value, the value of the function approaches a fixed value or infinity, but it never reaches there, right? So Y equals 0 is one horizontal asymptote. All right, that's good. That's finding number one. Let's say when E approaches 0, what happens? So is approaching 0, left-hand side will be negative Y cubed is a constant and positive number. So what does that mean? It means Y has to be, first of all, small, because E is small, is 0. And it has to be negative because we have negative y cube, right? So y has to be negative. In other words, we'll have a branch of the graph that will be in the negative y territory. And remember, y equals 0 is an asymptote. So I'm going to sketch something simple. It's going to look like this. So that's one branch. By the way, this is a cubic equation. So we'll have 3 roots, right? So in the vertical, we'll have 3 values for y. So this is the y negative kind of territory. Okay, so keep that in mind. Now, next one, I'm going to say when y approaches infinity, okay, then y squared approaches infinity. Okay, so if that's the case, e minus y will approach 0. And that means e will approach y. So again, what does that mean from a calculus standpoint? It means y equals e is your oblique asymptote. So we'll have an oblique asymptote at 45, right? y equals x. F of x is equals x is the 45 degree. So we have the 45 degree, and this will be our next asymptote. I'm going to say y equals e. Okay, so let's sketch the second branch of this graph. So it's going to be between y equals e and y equals 0 because those are the two asymptotes, right? And it's going to look like this. So it's going to asymptote, so it's going to approach that, and then something like this. Yeah, I didn't do a good job. I'm going to do it again. Let's try again. Yeah, I don't like it. Let's do it one more time. Yeah, that's much better. So that would be our EY graph for this given Q, for this specific Q, right? So, okay, so interesting. Let's look at this a little bit more detail. So at any given E value, somewhere here, what do we have? It's a cubic equation, so not a surprise. We have 3 values. We have one here, which is always negative. We have one here, relatively small y, and we have one here, relatively larger y. Now, obviously, depth cannot be negative. So it's safe and wise to assume that this branch, which is in the negative y territory, is not physically possible. So I'm going to say physically impossible. How can you have negative depth, right? So keep in mind, the specific energy equation is a cubic equation. You always have 3 roots, but one is the way it is set up. There's one will always be negative, and we'll stop talking about it from now on. We'll never talk about that negative root for obvious reasons, because from a practical standpoint and engineering standpoint, yeah, there's no point. It's not relevant. We cannot have negative depth. And there's 2 more left, 2 more positive roots or y or depth values. And those are the ones that we're going to discuss and talk about all the time. So I may not never again mention the negative y value, but keep in mind, it is there. We just don't really take it into consideration because it's impossible, physically impossible. And the 2 positive y values, depth values that we have, for now, just notice that one is a relatively small number and relative depth, and the other one is relatively large. Compared to each other, they're kind of that's how kind of they're set up, right? So it is the kind of the general graph of the EY curve. I want everybody to, we're going to talk about this a lot of time and sessions in the future too, but start kind of trying to visualize this and familiarizing yourself with this graph, because not only it helps with kind of knowing what is E, what is Y, but it helps with problem solving as well. There are actually methods that rely on graphical and visualization only, like just using graphs. We'll look at some examples, but Keep in mind, this is what it looks like. Asymptote at y equals 0, asymptote at y equals e, negative roots. We won't really discuss them. And very, very important to keep in mind, this is for one Q value. If Q changes, we'll have a new graph. So we have to sketch that. It will have the same properties. It will look the same. We'll look at how it changes the graph, but it won't be different shape. It will just be located at different location and slightly different shape. But generally, the two asymptotes will be there. It will look generally the same. We'll still have two roots and so on, right? Before we move on, one thing which is very important and worth mentioning is that if you look at this graph and say, okay, what if my specific energy is here? What if I have a specific energy of this value? Then what is depth for this specific energy? Because it doesn't have any intersection with the EY graph. So what does that mean? It basically means, again, we'll discuss this in detail, but it basically means that for that given specific energy E value that you're looking at, and this given fixed discharge Q that we have, that depth is not possible. All right. So another observation, another important point out of this EY graph is that it's not the domain and range, I should say range, if you're looking at y as the dependent variable, is not all numbers. Some numbers, obviously the negative ones are not possible, but also it has a minimum depth for any given Q. The depth cannot be less than whatever this value is. Here, I'm going to highlight it here. Right? Anything to the left of this line for this given Q is not possible. Right? So these are just observations from graph and calculus type standpoint. We'll look at these from hydraulics. What do they mean? What does it mean that it's not possible? And what happens if that is the case, and how do we deal with that? Well, we'll see them later, but as very basic first glimpse at this graph, these are things that we learn. Negative branch, we ignore it. Two positive roots. It has a minimum depth for a given Q, and below that, less than that discharge, less than that depth is not possible for a given Q. And also this graph is for one given fixed Q. If Q changes, the graph will change. We'll see how, but that's something that we'll need to discuss and learn. But so far, these are kind of the observations we have from the EY graph.